High above Chile's Atacama Desert, beneath some of the darkest skies on Earth, a remarkable machine is beginning to change the way humanity watches the universe. It is called the Vera Rubin Observatory. And unlike most telescopes, Rubin was not designed simply to stare at one distant object for hours or days. Its job is much bigger. It is designed to keep returning to the same sky, again and again. Every few nights, Rubin surveys enormous sections of the southern sky and compares what it sees with previous observations. If an asteroid moves, Rubin can notice. If a star suddenly becomes brighter or dimmer, Rubin can notice. If something new appears, Rubin can flag it. And if something that was once visible suddenly disappears, that can become a discovery too. This changes the basic way we think about astronomy. For thousands of years, humans looked upward and imagined the stars as permanent landmarks. The constellations seemed fixed. The galaxies seemed frozen in the distance. The night sky appeared almost timeless. But that was largely because human eyes could only capture tiny pieces of its story. The universe was never actually still. It was simply changing too slowly, or too subtly, for us to notice. Rubin is designed to change that. Its major project, the Legacy Survey of Space and Time, will repeatedly photograph the southern sky over many years. Instead of creating one enormous collection of isolated pictures, scientists will be able to compare observations taken at different moments. The result will be something closer to a time-lapse movie of the cosmos. A moving point of light could turn out to be an asteroid. A sudden burst of brightness could reveal a stellar explosion. A faint structure could expose an ancient collision between galaxies. And an object that disappears could point toward an event that cannot be seen directly. That ability to detect change is what makes Rubin so unusual. Telescopes such as Hubble and the James Webb Space Telescope have transformed our understanding of the universe by revealing incredible detail and allowing scientists to study light that comes from extremely distant and ancient objects. Rubin approaches the problem differently. It is built to watch a huge area of sky repeatedly. Its strength is not simply seeing farther. It is remembering what the sky looked like before. And some of its earliest observations have already shown why that matters. One of Rubin's first public images revealed an enormous number of galaxies packed into a single view of the Virgo region. We are not talking about millions of individual stars. We are talking about millions of galaxies. Each galaxy can contain billions of stars. Many of those stars may have their own planetary systems. Some may contain black holes. Others may have environments completely unlike anything found in our own galaxy. Yet from our perspective, these enormous systems can appear as tiny points and faint patches of light. And this is only a small glimpse of what Rubin is expected to observe during its long-term survey. But the number of galaxies is not the only thing that makes the images important. Hidden inside wide-field observations are structures that can be incredibly difficult to detect. One example is a stellar stream. These are long, faint trails of stars that can form when gravity pulls material away from a smaller stellar system. Imagine a smaller galaxy or star cluster passing too close to a much larger galaxy. The larger galaxy's gravity can stretch the smaller system apart. Over enormous periods of time, its stars can spread into a thin river extending across space. These streams are more than beautiful patterns. They are evidence of the violent history of galaxies. They can reveal ancient encounters, mergers, and gravitational interactions. They also provide clues about how dark matter influences the movement of stars. The problem is that stellar streams can be incredibly faint. Their light can be spread across such a large area that they almost disappear into the background. Older surveys could miss structures like these simply because they were too wide or too dim. Rubin's combination of a huge field of view, sensitive instruments, and repeated observations gives astronomers a much better chance of finding them. And then there are the objects much closer to home. Asteroids. Rubin's early observations have already helped identify thousands of previously unknown asteroids, providing a preview of what its full survey could eventually accomplish. Scientists expect the observatory to discover enormous numbers of small bodies throughout the solar system. That matters for more than astronomy. Asteroids are leftovers from the formation of the solar system. They preserve clues about the material that existed before the planets reached their current forms. By studying their orbits and physical properties, scientists can reconstruct parts of our solar system's ancient history. Some asteroids also pass relatively close to Earth. Finding them earlier gives researchers more time to determine where they are going and how their paths may change. But the most interesting objects are sometimes the ones that refuse to behave the way scientists expect. Consider a large asteroid rotating at an unusually high speed. When an object spins rapidly, centrifugal forces work against its own gravity. For a loosely assembled pile of rock, there is a point where rotation could become fast enough, and perhaps that is the most important thing Rubin has revealed so far. The universe was never a still picture. We simply lacked the ability to watch it properly. For centuries, astronomers had to choose where to look and when to look. A telescope might spend hours studying one galaxy, while countless other events were happening elsewhere at the same time. A star could brighten and fade. An asteroid could pass through the solar system. A distant object could disappear. And nobody might notice. Rubin changes that equation by turning the entire visible southern sky into a long-term observation project. Instead of asking only, "What is out there?" astronomers can also ask, "What changed?" That second question could prove to be even more powerful. Imagine looking at the same patch of sky thousands of times. At first, every image might appear almost identical. The stars are in familiar positions. The galaxies remain in the background. Nothing seems unusual. But when computers compare one image with another, tiny differences begin to emerge. A small point moves. Another becomes brighter. A faint object appears. Something else becomes weaker. A distant galaxy develops a temporary burst of light. Each change becomes a clue. And when millions of observations are combined, those clues can reveal an entirely different version of the universe. This is where Rubin's enormous data output becomes both exciting and challenging. A survey this large will produce an extraordinary number of alerts whenever something changes in the sky. Humans cannot manually examine every single event. Instead, automated systems will help identify the most interesting changes and send them to researchers for further investigation. Some alerts will turn out to be ordinary. Others could reveal something completely new. That is the nature of a survey like this. Most discoveries do not announce themselves with a giant sign saying, "New physics." Sometimes the first clue is simply a dot that moved slightly differently than expected. That dot might be a previously unknown asteroid. Or it could be a much more unusual object. One of the biggest advantages of Rubin is its ability to connect observations taken at different times. A single photograph can tell you where an object was. A sequence of photographs can tell you how it behaves. And behavior is often where the real information is. Take supernovae, for example. These enormous stellar explosions can become incredibly bright for a limited period before fading away. If a telescope happens to be observing the right region at the right moment, it can catch the event. But Rubin's repeated surveys increase the chances of discovering such transient events across huge areas of sky. That creates opportunities to study how stars die, how elements are produced, and how exploding stars affect their surrounding environments. Some supernovae are also useful as distance indicators. By studying them across enormous cosmic distances, astronomers can investigate how the universe has expanded over time. So an event that lasts only a relatively short period can become a tool for measuring the history of the cosmos. But there are events that may be even more difficult to identify. Gravitational microlensing is one example. Sometimes a massive object passes almost directly between Earth and a more distant star. Its gravity bends the background star's light. For a while, the distant star can appear brighter. Then, as the alignment changes, the brightness returns to normal. The event may last days, weeks, or longer depending on the objects involved. If astronomers detect the pattern carefully, they may be able to infer the presence of an otherwise invisible object. That could include a faint star, a distant planet, or another compact object. In some cases, gravitational microlensing can reveal planets that would be extremely difficult to detect using other techniques. This means Rubin could help expand our understanding of planets not only around nearby stars, but across much larger portions of the galaxy. And there is another category of objects that Rubin may dramatically increase our knowledge of. Small bodies in the outer solar system. Beyond the familiar planets lies a huge population of icy and rocky objects. Many are extremely faint. Some travel along unusual orbits. Others may have spent billions of years far from the Sun. Finding more of these objects could help scientists investigate the architecture of the outer solar system. Their orbits may contain clues about how the giant planets moved during the solar system's early history. Some unusual orbital patterns could even point toward gravitational influences that are difficult to explain. This is why discovering more objects is not simply a matter of adding names to a catalog. Every new orbit gives scientists another piece of evidence. And when thousands or millions of objects are studied together, patterns begin to emerge. Those patterns can reveal how the solar system formed. They can show how material moved through it. And they can help scientists understand why our planetary neighborhood looks the way it does today. But Rubin's reach goes far beyond our own galaxy. It may also transform how we study the Milky Way itself. Our galaxy contains an enormous number of stars spread across a vast disk. Many of those stars are faint. Some are hidden behind dust. Others are located in distant regions that have not been mapped with the same level.